Welcome to Lecture 6.1, Reducing Rational Expressions to Lowest Terms. In the next several lectures, we're going to start talking about rational expressions. So let's take a few steps back and recall what a rational number is. A rational number is in the form of a over b, where a and b are real numbers, are integers, and b is not 0. So the numerator can be any real number, and the denominator can be any real number besides 0. In the same idea, a rational expression is any expression that can be put in the form p over q, where p and q are polynomials, and q does not equal 0. For definition, you can see how it's written, just p over q, where p and q are polynomials and q does not equal 0. That's the official definition of a rational expression. So for example, 2x plus 3 all over x, is a rational expression. X squared minus 6x plus 9 all over x squared minus 4 is a rational expression. 5 over x squared plus 6, rational expression, and 2x squared plus 3x plus 4 all over 2 is a rational expression. We still use the term for the value on the top of the fraction as the numerator, and the bottom is the denominator. For example, 2x plus 3 all over x, the numerator is 2x plus 3, and the denominator is x. But here's where it differs. The denominator cannot be 0, so there's a restriction as to what x can equal in this example. And in this case, x cannot equal 0. It could be anything else, but not 0. So to find the restriction on any rational expression, we're going to set the denominator to 0 and then solve for the variable. Now if the denominator is already constant, then we don't care. There's no restriction. So if it's a 2, there's no restriction. If it's a 100, there's no restriction. It's just when there is a variable in the denominator, then we need to figure out what is the restriction on that variable. For example, let's figure out what the restriction on the variable is when we have x plus 2 all over x minus 3. Because the denominator cannot be 0, I'm going to set the denominator not to equal 0. X minus 3 shouldn't equal 0. So x cannot be 3. It could be everything else, but it can't be 3. The moment that it's 3, 3 minus 3 is 0. Let's try another one. Let's state the restriction on 5 all over x squared minus x plus minus 6. First thing I'm going to do is factor that denominator. So I get x minus 3 times x plus 2, and we do not want it to equal 0. So I'm going to break both of those apart and see what it shouldn't be. So x minus 3 shouldn't be 0, and x plus 2 shouldn't be 0. Therefore, x can't be 3, x can't be negative 2. It can be everything else but those two numbers. We have a few properties at our disposal with rational expressions, and they'll probably sound very familiar to you because we use this with fractions. So the first one is multiplication. If we multiply the numerator and the denominator by the same non-zero quantity, it's not going to change the rational expression. Likewise, if we divide the numerator and the denominator by the same non-zero quantity, it will not change the value of the rational expression. Both of these still hold true with rational expressions, just like they did with fractions. For example, if I had a fraction of 10 over 12, I could factor both of those into 2 times 5 for the numerator and 2 times 6 for the denominator. Well, 2 over 2 is just a 1, so I can divide that out, and it doesn't change my expression. It looks a little different, but the value is exactly the same. 5 over 6 is the same value as 10 over 12. Likewise, with rational expressions, if I divide out what the numerator and the denominator have in common, I really don't change the quantity at all. So applying these properties, we can reduce rational expressions to the lowest term. So first I'm going to factor the numerator, I'm going to factor the denominator completely, and then I'm going to divide both the numerator and the denominator by any factors they have in common. For example, let's reduce x squared minus 9 all over x squared plus 5x plus 6. And we want to reduce this to its lowest terms. I'm going to factor the numerator, factor the denominator. So x squared minus 9 factors into x plus 3 and x minus 3. X squared plus 5x plus 6 factors into x plus 3 and x plus 2. But I can see the numerator has an x plus 3, the denominator has an x plus 3. Well, anything over itself is just a 1, so I can cancel those out, leaving me with the lowest term would be x minus 3, x plus 2. Here's a very common mistake. What will happen is that you'll see, oh, this has an x squared, and this has an x squared, so I'll just cancel that out. No. Because this x squared is attached to something else, so it is not the same thing. This x squared on top is not the same x squared that's on the bottom. You must factor it and see what factors they both have in common. It's very similar to saying 2a all over 2b. A and b are not the same, although they're letters. I can't just cancel them out. Or I can't cross over that addition or subtraction. It's all of it meshed into one. They're apples and oranges. So until I can get it to look like something very similar by factoring, then I can see what they really have in common. Because as you see, if I would have just crossed off the x squared and the x squared, that would leave me negative 9 over 5x plus 6. That's certainly not the answer that is the true correct answer. X minus 3 is not a negative 9. And x plus 2 is not a 5x plus 6. So be very careful. Factor first. Just don't look at it and say cross, everything's gone. No, you have to factor it first. Let's try another example. Let's reduce to the lowest terms 10a plus 20 all over 5a squared minus 20. This is another case where you might want to jump in and do the 20 over 20, but you have to remember, it's not just a 20. There is addition here. It's not just a 20, there's subtraction here. So it's all of this together. So I'm going to factor both the top and the bottom. I can factor out a 10 for my GCF for the numerator. I can factor out a 5 in my denominator. And then the numerator is completely factored, but the denominator, I can factor the a squared minus 4 into a plus 2 and a minus 2. Now I see they both have an a plus 2 in common, but the 10 can be factored into 5 and 2, so they both have a 5 in common as well, leaving me with 2 all over a minus 2. Let's try a couple more. Let's reduce to lowest terms 2x cubed plus 2x squared minus 24x all over x cubed plus 2x squared minus 8x. So I'm going to factor both the numerator and the denominator. First thing is, do I have a GCF? Do I have a greatest common factor? Both the numerator and the denominator have greatest common factors. The greatest common factor of the numerator is 2x. Greatest common factor of the denominator is x. Now I need to factor each of the parentheses. And therefore, 2x cubed plus 2x squared minus 24x factors into 2x times x plus 4 times x minus 3. X cubed plus 2x squared minus 8 factors into x times x minus 2 times x plus 4. Now they both have an x plus 4 in common, and they both have an x in common. So I can cancel those out, leaving me in the numerator 2 times x minus 3, and in the denominator x minus 2. Let's reduce x minus 5 all over x squared minus 25. So the x minus 5 is already factored. There's nothing else to factor, but the denominator can be x minus 5 or x plus 5. I have x minus 5 over x minus 5. Remember, there is an implied, it goes in once, it goes in once. So I have an implied 1 there. So my final answer is x all over x plus 5. A ratio is a fraction, so if a and b are any two numbers and b does not equal 0, then the ratio of a and b is a over b. If you consider this line to mean 2, so a to b, as in T-O, not the number 2, a to b, then you know what's the numerator will be a, 2 is the line, and b is the denominator. So let's take in consideration some ratios. 25 to 75. Well, as a fraction, that's 25 over 75. In lowest terms, that's 1 to 3, or 1 over 3. 8 to 2 is 8 over 2. In lowest terms, that's 4 over 1. 20 to 16 is 20 over 16, and we can reduce it down to 5 over 4, or 5/4. Let's try an example with ratios. So a solution of hydrochloric acid, HCl, and water, H2O, contains 49 milliliters of H2O, aka water, and 21 milliliters of HCl, aka hydrochloric acid. Let's find the ratio of hydrochloric acid to water and hydrochloric acid to the total amount of the solution. So there's two problems here. Let's work on the first problem, HCl to H2O. Well, HCl to H2O, which means the amount of hydrochloric acid to the amount of water, so that's 21 to 49. So 21 over 49, and let's reduce it to 3/7. Now the hydrochloric acid to the total amount of the solution, we're not given the total amount of solution, but we do know it's going to be the water plus the hydrochloric acid. So hydrochloric acid is 21 milliliters, and the total amount of solution is going to be 49 plus the 21, giving us 70. So the ratio of 21 to 70, or 21 over 70, will reduce to 3 over 10. Now you might remember the rate equation. Distance equals rate, which is the average speed, times time, or D equals R times T. Now, of course, there's three ways to write this up. I can have it equaling the distance, which is distance equals R times T. I can equal the rate, which is distance divided by time, or time, which is distance divided by rate. So let's take in consideration this problem of the forest chairlift at the North Star Ski Resort in Lake Tahoe is 5,603 feet long. If a ride in the chairlift takes 11 minutes, what is the average speed for the lift in feet per minute? Since I'm looking for the rate of speed, I'm going to use this R equals D over T. My unknown is my R, so I might as well use the distance over time. My distance is 5,603 feet. My time is 11 minutes. I'm just going to do that division, which is 509 feet per minute. So that's it for this lecture. So until next time, be seeing you.